Hey guys, so I want to talk about general potential energies, things which aren't just constants or lines. So in general, you could imagine any smooth function, any differentiable function, and you can imagine taking its derivative to produce, or minus its derivative to produce a force. So an arbitrary potential energy, if you're familiar with chemistry, you see pictures like this for potential energy versus X, and I don't know, it looks something like that. Okay, some sort of weird roller coaster sort of problem. And so when you see a graph like this, you might think, oh, I don't even know what that would mean. So what you can do, though, is just use what you know about calculus. We know the relationship between force and potential energy. Specifically, we know that forces, conservative forces, are minus derivatives on energies. So let's just apply that concept to this curve. So let's imagine that someone was standing right here. Okay? At this point on the curve, the slope is negative. If the slope is negative, so this derivative is negative, just a second here. Okay, sorry about that. I had a telephone call. All right, so let's imagine that you're standing here on the dot. Man, I just can't get away from these spots. You're standing on the dot at a place where the slope is negative. So if the slope of the potential energy graph is negative, the force would actually be positive. So that means if you stood right here, you would feel a force to the right. On the other hand, if you were over here at a place where the slope was positive, if the slope is positive, the force you would feel would be negative. It would push you back to the left. So, that's interesting. So when you feel a force, when you're on one side, you get pushed forward, and you're on the other side, you get pushed back. And in fact, if you're in a place where the slope is zero, if the slope is zero, then the force is zero. This is called equilibrium. And in particular, this is a stable equilibrium point. If you put an object here, I don't know what this curve really represents, but if you put something here at the minimum, if it goes to the right, it gets pushed back. If it goes to the left, it gets pushed forward. And if it's placed right at the minimum, it stays still. That is a stable equilibrium. Meaning if you perturb it a little bit, the particle doesn't wander off somewhere else. You can contrast that with the point that is up here at the top. This would also be an equilibrium point because the slope is zero, but it is an unstable equilibrium point. If someone were to sneeze, achoo, and bump you infinitesimally over to the side, you get runaway behavior and it wants to roll away. So this is an unstable equilibrium. Okay? Stable equilibrium and unstable equilibrium. So those concepts come up all the time in chemistry, and you might have been wondering, we've been talking about forces, and forces are supposed to describe everything. How does chemistry pop out of all this stuff? And I mean, that's a complicated story involving lots of things, quantum mechanics and statistical treatment of collections of atoms and things. But you can kind of see the precursor to what's eventually going to happen. You're basically saying, all other things being equal, forces push you to lower potential energy. And that's a good way to remember it. When you have a conservative force, it pushes you in the direction of lowering your potential energy. So if I drop this, as it falls, the potential energy is lowered. Guess what? Gravity has a force which acts downhill in potential energy. So forces point in the direction of lower potential energy. Another observation, if you were to move around from one value of x to another value of x and you come back to the same place, well, the potential energy might increase, but then if you come back to where you started, the potential energy does not change. So, and more generally, when you have potential energy, the way that you go from place to place does not affect the change in the amount of potential energy. It's said to be path independent. So the change in potential energy of gravity only depends upon the height. So mg delta y is the change in potential energy. So I can do any sort of path, loop-de-loop, round and back, behind my head, behind my back, whatever. If you have the same change in height, you get the same change in potential energy. So that's an interesting observation. Okay.